Okay, so in this video, we will consider our second counting setup. As always, the problem is the same. We want to count the number of ways in which R elements may be selected from a set containing n elements. The setup now is the following. The selection will be ordered just as setup 1, but if you remember, setup 1 was with replacement. Now setup 2 is without replacement. So let's try and count again the total number of ways in which R elements can be selected from n elements under this setup. So as always, you can visualize your elements as being balls numbered from 1 to n. Because again we have an ordered setup, this gives us again a Cartesian product. So we have to look at the first selection, then the second, then the third. Because we are selecting our elements, we have our choices. Just as in setup 1, as it is still ordered, but now it is without replacement. So let's see. We're trying to count all possibilities of selecting our elements from a set of n elements when we keep track of the order of the selection, but now without replacement. So here for the first pick, well, we have n options. Just for argument's sake, suppose it was ball number 1. Now, because it is without replacement, ball number 1 is no longer available for our second choice. Therefore, here we do not have n options again, but we have one fewer, therefore n minus 1. Just for argument's sake, suppose that ball number 2 was drawn. Because it is again without replacement, ball number 2 is no longer available. So for the third pick now, we have 2 fewer options, so we're down to n minus 2. And you see where this is going, n minus 3, n minus 4. The only question is, where does this end? And you have to be careful. You see, this was our first pick, our second pick, our third pick, and we end to the rth pick, as there are r choices. Now if you think of it, here we do n minus 1 plus 1 to get n. Here we do n minus 2 plus 1 to get n minus 1. Here we do n minus 3 plus 1 to get n minus 2. So here when we end at r, we do n minus r plus 1. And that's it. So the total number of ways in which we can select our r elements from n elements, given an ordered setup and without replacement, is. And we denote this in a special way. We write n, p, in uppercase p, and then lowercase r, and this simply reads npr, which stands for the total number of ways in which r elements can be selected from n elements when the setup is ordered and without replacement is equal to. Well, let's see. We have n options for the first pick, and times n minus 1 options for the second pick, and times n minus 2 options for the third pick, and times. Finally, n minus r plus 1 options for the final pick. And that's it. But you can imagine now that we don't want to leave it like this. Because what if n was, say, 1000 and r was 400? This would be a pretty long product. And we wouldn't want to calculate this as this is with our calculation. With our calculator, sorry. This would be way too long. Let's see if we can condense this into a more manageable formula. And the answer is yes. We have to be a little tricky about this. The idea is, let's extend this. So NPR equals n times n minus 1 all the way down to n minus r plus 1, and I will keep going. You see, every step we subtract 1, so we'll have n minus r plus 1 minus 1, so n minus r. Now you keep subtracting until you reach down to 2 times 1. But of course now we're cheating. We are changing the original answer, which was this product right here. So if you multiply by something, the only way to cancel it back is to divide by it. But now if you look at this can be written quite concisely. Start from here. 1 times 2 times 3 times 4 all the way up to n. This is the product of the first positive n integers. This is by definition simply n factorial. And look on your denominator. 1 times 2 times 3 times 4 all the way up to n minus r. This is the product of the first positive n minus r integers. And by definition, therefore, is n minus r factorial. So there you go. NPR is simply n factorial over n minus r factorial. Now let me show you a calculation with the standard sharp calculator, and you'll see that there is a short key NPR on the calculator, or you could also use the factorial, but this will be faster with the short key. So always remember, NPR stands for the total number of ways in which R elements can be selected from n elements if the selection is ordered and without replacement. So let's do now, let's say 9p5. So we are asking to count here the total number of ways in which 5 elements can be selected from a set of 9 elements with an ordered selection and without replacement. So here's your sharp calculator. This is the standard model, at least a standard model. And if you look above the key 6, you see NPR. So you type in your n first, 9. Because you're above the key of 6, you have to use your second function. Press 6, 9p, the p appears. And now you want, of course, 9p5, press 5, equals, and you see 9p5 is 15,120. And that's how you can use a shortcut key on the calculator to calculate the so-called permutations. Or you could use the factorial. So 9p5, well, if you use our factorial, it is 9 factorial over, and here be careful, it's not r, it's n minus r. 9 minus 5 is 4 over 4 factorial. Now the shortcut key for factorial is above the 4, so you would simply do 9 second command 4 9 factorial divided by 4 second command 4 4 factorial, and you will get once again 15,120. But you're better off with the short key directly, as it avoids you computing these two factorials. Okay, let's consider now two examples. One where we can essentially go around NPR, but then you'll understand why NPR is fundamental, and we've already in a sense explained this, as if n and r are very large, this would take a long time to calculate one number at a time in our calculator. Okay, so here's the problem. An urn contains balls numbered from 1 to 10. First, let's visualize this. We have an urn. that contains 10 balls numbered from 1 to 10. So here n is 10. The total number of elements we can choose from, there are 10 balls. So part A. If you randomly select 6 balls, one after the other, and record the ordered selection, the ordered result. So here we're told that we have an ordered selection. We are asking how many outcomes are possible. So here, the implication here, and this is implicit, is that once you pick a ball from this urn, you can't put it back in, right? We're saying you randomly select 6 balls, one after the other, and record the ordered result, how many outcomes are possible. So implicitly here, it is without replacement. So we are under the right setup. An ordered selection without replacement. Well, how many balls are we selecting? We're selecting 6 balls. So R is 6. And so we are asking how many possible outcomes are there? Well, this is NPR. So NPR, again, because we are under the right setup. An ordered selection without replacement. So this is 10 P6. Using the shortcut key on your calculator, you'll find 151,200 and different possible selections. Let me show you that even if you didn't know about NPR, you could have arrived at this answer just by brute force, by visualizing your selection. So, or, this is the long way, we're selecting 6 balls. So ball number 1, 2, 3, 4, 5, 6. Again, we have a Cartesian product, a sequence of choices as we have an ordered selection. Because it is without replacement, we have 10 options first, but whatever we picked for the first ball, we can't pick again for the second ball. So it's 9, and the same goes for the third ball, 8, 7, 6, 5. So, the total number of ways in which we can select 6 balls from 10 balls, when we keep track of the order of the selection, and it is without replacement, would be 10 times 9 times 8 times 7 times 6 times 5. Oop. And if you multiply this out with your calculator, you will arrive at the same answer. But that is the long way of doing it. But it's not that bad. B, what are we asking in B? How many outcomes are there with the second ball being a 3? So we're told that the second ball is 3, and the fourth ball being 1. So let's visualize. We're told that the second ball is a 3, which means that there's only one choice for the second ball. It must be a 3. And the fourth ball is a 1. The fourth ball is a 1. And so there's just one choice here. So if you think of it, we are left with 1, 2, 3, 4 choices. Out of how many? Well, we have originally 10 choices, but it is without replacement. So these 2 balls now are gone from our other possible choices. So instead of 10 choices, we're left with 10 minus 2, 8 choices. So 8 possible numbers to choose from, and we are choosing 4. Again, the selection of these 4 choices, 1, 2, 3, 4, is ordered, and without replacements, it's simply 8p4. With your calculator, using the shortcut key, you will arrive at 1,680 possible such selections. Or, you could also brute force it and not using the NPR shortcut. If you think of it, well, we're left with 8 choices for the first ball, 7 for the third, 6 for the fifth, and fifth. 5 options for the sixth pick. So we have in total 8 choices first, then 1, then 7, then 1, then 6, then 5. And if again you punch this out in your calculator, you will arrive at the same answer. Okay, so now you can ask, of course, well, if we can find the answer brute force, and it's a little bit more work, but not that much more work, why do we bother with NPR? Well, as we've said before, what if we had 1,000 balls to choose from, and we chose, say, 200? This would be a very long product. And so punching this in our calculator would just take up way too much time. And so we'd use, obviously, the shortcut key formula. So let's look at an example of this where we will not want to do it brute force, but do it properly with NPR. So same problem as number 1, except now we are saying that our urn contains balls numbered from 1 to 30. So 3 times as many balls as problem 1. Okay, so here we're saying that in part A, well here of course n is 30. There are 30 balls to choose from. So if you randomly select 22 balls, so here are the number of elements being selected is 22, one after the other, and record the ordered result, which means that we have once again an ordered selection. How many outcomes are possible? And again, implicitly here, once we draw a ball, it's no longer available for a second pick. So it is again a setup that is ordered and without replacement. So it's again the setup of NPR. So the total number of possible outcomes is NPR, N is 30, and R is 22. Once again, punch this into your calculator, and you will arrive at and I'll write approximately because the number is really big. So it's going to be approximately 6.5787. You'll see why I'm rounding off here, times 10 to the 27. So this number is huge, but it's approximately 6.5787 times 10 to the 27. So you're multiplying this number by 10 27 times. It's a huge number of possible outcomes. Now, think of it as looking at this from a naive point of view by trying to find the total number of possible outcomes brute force. You would say, okay, well, we have our first pick, our second, our third pick, up to pick number 22. We have 30 options for the first pick, 29 for the second, 28 for the third, as again we are without replacement, up to, here this is going to be 30, minus 22, 8, plus 1, 9. So your number would be 30 times 29 times 28, all the way down to times 9. And if you would multiply this out, so 9 times 10 times 11 times 12 times 13, all the way up to 30, you will arrive at the same answer, 30p22, which is approximately this number. But this is an incredible waste of time. And that's why we came up with this idea that is, again, a shortcut formula. Instead of multiplying all of these out, 30p22, and the calculator does it for you. So much more efficient. So this is still possible, but a really bad idea. Way too long. Same for B now. We're asking how many outcomes are there with the second ball being 3 and the fourth ball being 1. let's visualize. So ball number 1, 2, 3, 4, 5, up to ball number 22. The second ball being a 3, which means only one option for the second ball, and the fourth ball being a 1. So again, only one option for the fourth pick. So if you think of it, that leaves you with how many balls? Well, as it is with that replacement, we have 30 minus 2 balls, therefore 28. There were 22 picks in total, but 2 have already been made, and so we're left with 22 minus 2 picks, therefore 20. And again, the selection is ordered, and again without replacement. So it's simply the total number of possible such selections is 28p20. And if you punch this in again, it's a very large number. So rounding off, it is approximately 7.5617 times 10 to the 24. So again, a huge number of possible outcomes. But with the shortcut formula, this takes 2 seconds to punch in and to get the final answer. So always remember this. If you are selecting R elements from a set of N elements, and the selection is ordered and without replacement, the total number of possible ways in which this can be accomplished is just N PR, which can be obtained from the shortcut key in the calculator, or if you prefer with the factorial, N factorial over N minus R factorial. Don't ever multiply this out one number at a time on your calculator. That is an incredible waste of time. Use NPR. In our next video, we will consider our final setup of counting, now where the selection is unordered and without replacement.